Let's study 9th standard ICSE chemistry, chapter 5, the periodic table. Everything on earth is made up of these 118 elements. In fact, some of them does not even exist naturally on earth. They don't. They are artificially prepared in the laboratory, especially the elements after uranium. The most abundant elements in earth are oxygen, aluminium, iron, silicon, carbon, etc. But what is an element? It is the simplest form of matter which cannot be chemically decomposed into simpler substances. There was a time when people believed that water is an element. But now we know that it isn't, because it can be chemically decomposed to give you hydrogen and oxygen gases through a process called electrolysis. But hydrogen and oxygen respectively cannot be decomposed further by any chemical method. Hence they are elements. You can see that most of the elements are metals. Few of them are metalloids, which have properties of both metals and nonmetals. And the nonmetals are also very few, mostly in the gaseous state. In the periodic table, the modern periodic table, there are totally 18 groups and 7 periods. If element number 119 is discovered or created, then that will be the beginning of the 8th period. So good luck with that. Now, arranging the elements in groups and periods makes studying their properties very easy. It gives us a systematic classification, just like we do classification in the animal and plant kingdom in biology. Notice some features of this periodic table. The first period is the shortest with only 2 elements, hydrogen and helium, and hydrogen's position is disputed because it has properties like the alkali metals and even the halogens. And by halogens I mean salt generators, halogen. Group 18, which was earlier called group 0, consists of noble gases. They are almost inert. They hardly react with any other element unless the conditions are extreme. Their last shells are complete. Helium has 2 electrons in its last shell, which cannot accommodate any more electrons, so it's stable. It won't lose or gain or share electrons with any other atom. It doesn't need to. It's a monoatomic molecule. Neon, atomic number 10, has electronic configuration 2,8. So it has 8 electrons in the last shell. So it has a stable electronic configuration. The last shell is complete with an octet. So it won't react with any other element. And that's true for all these noble gases. You need to know at least the first 20 elements in order, so that you know their electronic configuration. And the electronic configuration gives us a lot of information. Look at element number 13, aluminium. Its atomic number is 13. That means its electronic configuration is 2,8,3. Which means its last shell consists of 3 electrons. You can draw the structure like this. In order to achieve the electronic configuration of the nearest noble gas, and in this case that is neon, 2,8, it would give the 3 electrons in the last shell. It will lose electrons. It will undergo oxidation, that is, it will lose electrons to a nonmetal, so that its electronic configuration becomes 2,8 and it becomes stable. But if it does that, then it will have only 10 electrons left, whereas the number of protons in its nucleus would still be 13. So the atomic number is actually the number of protons, which is the identity of an element. It is a fundamental characteristic of any element, because the atomic number decides the electronic configuration, which decides the valency, which decides the chemical properties of an element. Metals usually have 1, 2 or 3 electrons in the last shell. They lose electrons and become cations, positively charged, because after losing electrons, which are negatively charged, the number of positive charges becomes more than the number of negative charges. So it becomes a cation. And in this case, it will have 3 positive charges after losing the 3 electrons. The number of neutrons are not fixed in the nucleus of an atom. It may vary. That's why the mass number may change. And it is not a fundamental characteristic, because the number of neutrons don't affect the chemical properties of an element. The mass number is a total of the number of protons and number of neutrons. So since the number of neutrons can change, mass number can also change, even though the atomic number for a given element is always fixed. That is, number of protons for a given element is fixed. So if the mass number is different, they are called isotopes. For example, oxygen has atomic number 8 and mass number 16. So 8 protons and 8 neutrons. Number of neutrons is given by mass number minus atomic number. And of course it has 8 electrons, 2,6. That's why it's neutral. It's electrically neutral. There are some oxygen atoms which have 10 neutrons. So the mass number becomes 18. That is called an isotope of oxygen. So isotopes are atoms of the same element with the same atomic number but different mass number. So they will have the same chemical properties because electronic configuration is the same, but they will have slightly different physical properties like density, boiling point, etc. Now, oxygen atom has 6 electrons in its last shell, the valence shell, and in order to achieve the stable configuration of the nearest noble gas, which again in this case is neon, it would have to gain 2 electrons or maybe share 2 electrons. Then only it will have the electronic configuration 2,8. But if that happens, if it gains 2 electrons, then it will become negatively charged, because then it would have 10 electrons and 8 protons only. So more negative charge here. That's why it's a non-metal. And gaining of electrons is called reduction. So usually atoms with 5, 6 or 7 electrons in the last shell are non-metals. Yeah, if it's exactly 4, then it's mostly non-metallic. But in case of silicon, it's a metalloid. And beyond the 20 elements, we don't have to study right now because the rules are very different for the stability of atoms after calcium. In fact, many of the transition elements have something called variable valency. For example, copper may have valency +1 and also +2 because they do lose electrons not only from the last shell, but even the second last shell or the penultimate shell. But we don't have to get into it right now. We see that the second and the third period have 8 elements each with a gap in between. Then the fourth and the fifth period have 18 elements, and the sixth and the seventh periods have 32 elements, but 14 out of them are not mentioned here in the main table. You can see after 57 it has jumped directly to 72, and there is an asterisk out here, and there is an asterisk out here as well. This is called the lanthanide series. So all the elements, 14 elements after lanthanum, are the lanthanide series. All of them are supposed to be belonging to group 3, but you can't fit 15 elements in the same box. Hence, they have been written separately here. So all of them belong to period number 6 and group number 3. Similarly, after actinium, we have the actinide series. These 14 elements have properties very similar to actinium, so they should be placed in the same group number 3 and period number 7, but they've been mentioned separately. So period 7 also has 32 elements. But most of them are radioactive because they're very unstable. You can see the mass number is far greater than the atomic number. Number of neutrons are too much, and so they don't exist for a long time. They decompose, they decay into smaller elements very quickly. Group 1 elements are called alkali metals. They are very reactive. In fact, the reactivity increases as you go down the group, with cesium being the most reactive metal in the entire periodic table. Theoretically, francium should be even more reactive, but francium is so unstable that it doesn't last for more than a few seconds or minutes. So we can't study its chemical properties in detail. On the other hand, fluorine is the most electronegative or non-metallic element. They are diagonally opposite, as you can see. In case of halogens, the reactivity decreases down the group. And here the reactivity increases down the group. Such trends are interesting and important to be studied, which we shall do in this chapter. Group 2 are called alkaline earth metals, which are also very reactive, but slightly less reactive than the alkali metals. They are called alkali and alkaline because their oxides and hydroxides are basic in nature. In fact, if they dissolve in water, they form alkalis. The beauty of this periodic table is that elements belonging to the same group have the same properties or similar properties, which helps us to remember them. Also, as you go across a period from left to right, we see a gradation in their properties. Some trends are seen and tendencies are seen as far as atomic size is concerned, or the metallic and non-metallic character, etc. That's the advantage of this modern periodic table. But how was it created? It was a step-by-step process. There were many trials and errors, failures and successes. So let's start studying the history of classification of elements. The first type of classification we shall study is Dobereiner's triads. He classified the then known elements into groups of 3, like lithium, sodium, potassium. And the interesting thing he found was that the atomic mass of the middle element in the triad is almost the average of the atomic mass of the other two. So if you do 7 plus 39, that's 46. 46 upon 2 is 23, which gives us the atomic mass of sodium. So his law says that the chemically analogous elements, that is the elements with similar properties, they have similar properties, when arranged in the increasing order of the atomic weights, formed well-marked groups such that the atomic weight of the middle element was the arithmetic mean or the average of the atomic weights of the other two elements. But this method was discarded because it was not holding true for all elements at that time. It was just applicable in a few cases. And there were many triads formed where the average was working out, but then the properties were not same. The next attempt was made by Newland. The law of octaves says that when you arrange the elements in their increasing order of atomic weight, you will notice that the properties of the 8th element is always similar to the first element. So let's start with boron. If I assume boron to be the first element, then 1, 2, 3, 4, 5, 6, 7, 8. Aluminium is the 8th element, so its properties will be similar to that of boron. This is similar to a musical note, where the 8th note is just the next version of the first one. So this is called the law of octaves, which was quite fascinating. But it failed because it did not leave spaces for undiscovered elements. So if there are elements which were undiscovered, that would ruin the entire table. But Newland did not think about that at that time. So it was applicable for the lighter elements, that is for the first 19 elements. But beyond that, it failed for the heavier elements. And the next method was adopted by Mendeleev, and he is called the father of the modern periodic table because he was the first one to have some sort of a periodic table which looked something like this, pretty similar to the modern periodic table but not quite. So he had groups and periods, and he also used the logic that the elements belonging to the same group should have similar properties. And the master stroke he had was that if an element's property is not matching the properties of that group, then he wouldn't place it there. He would leave gaps and place it somewhere else. So this is the actual Mendeleev's periodic table. So he had left gaps for the discovery of elements, and no surprise, after a few years, those elements were discovered. And another act of genius was that Mendeleev had predicted the properties of these elements based on their position in the group. And when these elements were discovered, it matched the predictions. But there were a few flaws in this periodic table. First, there were some anomalies. For example, argon has an atomic mass of 39.9 and potassium has atomic mass of 39.1. So argon should be kept after potassium, but in his table it was kept before potassium. Second issue was about isotopes. Now oxygen's atomic mass is around 16, but there are some isotopes of oxygen whose atomic mass is 18. But the chemical properties are the same as oxygen, so it should be kept here and not in the next group. So the position of isotopes was quite confusing out here. Another problem was that sometimes chemically dissimilar elements were kept together. For example, lithium, sodium, potassium are alkali metals, but what are copper and silver doing in this group? Of course, the position of hydrogen was not fixed even then. That was another problem. And elements like gold and platinum, which are so similar, were kept far apart. Gold is here and platinum is here. So the problem with Mendeleev's periodic law was that he said the chemical and physical properties of elements are periodic functions of their atomic weights. What it means is that if the elements are kept and arranged in an increasing order of their atomic weights, then we will see periodicity in their physical and chemical properties, that there will be repetition. There is lithium, blah, 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 sodium, blah, 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 potassium. So lithium, sodium, potassium have the same properties. They have valency 1, they are metals, highly reactive, they form alkalis, etc. So the problem was that he was arranging them according to atomic weight. He didn't realize that the fundamental characteristic of an element is not the atomic weight, it's the atomic number. So it was Moseley who realized this, and he tweaked the law a bit, and now we have the modern periodic law, which says that the physical and chemical properties of elements are periodic functions of their atomic numbers. That means if we arrange the elements in the increasing order of their atomic numbers, we will see some periodic repetition in their physical and chemical properties. And why is atomic number so crucial for the properties of an element? Well, as I explained, atomic number decides the electronic configuration, and the outer electronic configuration is indeed the cause of all the chemical properties. And after regular intervals, you do see a recurrence in the electronic configuration. For example, if this is 2,1, 2,8,1, 2,8,8,1, and so on. Now let us study the trends in the periodic table. If you go from left to right, what happens with the number of shells? Well, it remains the same, isn't it? All the elements of period number 2 will have 2 shells. All the elements of period number 3 will have 3 shells. 2,8,1, 2,8,2, 2,8,3, all of them have 3 shells. In fact, the period number tells us the number of shells, and the group number tells us the valency. So group 1 has valency 1, and they're electropositive, that is, they will lose electrons. Group 2 has valency 2. Group 13 has valency 3. Yeah, group 3 to 12 are missing, because if you've checked, group 3 to 12 belong to the transition metals, which we don't have to study in our syllabus because the rules for them are more complicated. So group 14 will have valency 4, group 15 will have valency 3 again. Yes, valence electrons will be 5 electrons in the last shell. Group number helps us to understand the number of electrons in the last shell. 5 electrons in the last shell. But valency won't be 5, valency will be 3, because now they will gain 3 electrons or share 3 electrons to be stable. So group 16 will have 6 valence electrons and valency 2 again. Group 17 will have 7 valence electrons and valency 1 again, 1 minus if you talk about electrovalency. And group 18 has no valency at all. We also see that the metallic property decreases, becomes metalloid, and non-metallic property increases, and then group 17 has the most non-metallic property. So that's the trend we see. What about number of valence electrons? Obviously it increases by 1 valence electrons, 2 valence electrons, 3 valence electrons, 4, 5, 6, 7 and 8 valence electrons. That means number of electrons in the last shell. What happens down a group? Well, as you go down a group, the chemical properties are same because the electronic configuration is similar. The number of valence electrons is same, 1, 1, 1, 1, 1, 1. The number of shells increases, 2 shells, 3 shells, 4 shells, 5, 6, 7 shells, because 7th period. metallic character increases. This is the most metallic element theoretically, and practically this is the most metallic element. Hydrogen is not included in alkali metals because it's not really a metal, it's a non-metal, sometimes behaving like an alkali metal, so its position is not fixed. But why does the metallic character increase down the group? Well, that's something you will study in 10th standard. Hush, sigh of relief from you. So let's quickly summarize the characteristics which we have studied. Alkali metals, learn the list. They are highly reactive, electropositive. They are good reducing agents because, as I told you, they lose electrons, so they undergo oxidation. That means they reduce others, so they are good reducing agents. Always remember, metals are good reducing agents. Why? Because they lose electrons. They form strong alkalis. Same properties are there for alkaline earth metals too, but they're slightly less reactive. Group 3 to 12 are called transition elements because they show a transition from metallic elements to non-metallic elements, although they are themselves metals. Inner transition elements are the lanthanide and the actinide series, which were kept at the bottom of the table. We need to know the first and the last elements of each, and we should remember that all of them belong to group 3 and period 6 and period 7 respectively. Next, group 13 to 16 are called post-transition elements. They are mostly weak metals, metalloids and non-metals. Group 17 are called halogens. We need to remember the elements, and their valency is 1, although 1 minus. Highly reactive, and they're good oxidizing agents because if you remember, halogens, they accept electrons, that is, they get reduced. That means they are good oxidizing agents. And they are non-conductors of electricity because they are non-metals. Metals are good conductors and non-metals are bad conductors of electricity. Group 18 are called noble gases. Nowadays they are not called inert because they are not completely inert. For example, xenon, radon at very high temperature or pressure can be forced to react, but mostly they don't form any compounds at all. Now group 1, 2, 13, 14, 15, 16, 17 are called normal elements because they lose electrons only from the last shell, unlike group 3 to 12, which are transition elements and they show variable valency. Now something interesting here, there is something called bridge elements. If you look at the periodic table, yes, it's true that boron and aluminium have similar properties, but boron and silicon also have similar properties. In fact, both of them are metalloids. So this diagonal relationship between them is they are called bridge elements. Similarly, beryllium and aluminium have similar properties. So if we just skip this middle part here, then the beryllium and aluminium are called bridge elements. Remember, metals always form electrovalent compounds. That is, they lose electrons and the non-metal will gain electron. So the metal will become cation, the non-metal will become anion, and there will be electrostatic force of attraction between them, creating an ionic bond or an electrovalent bond. So as you can see here, electron is lost, electron is gained, and ionic bond is formed. Alkaline earth metals are also light metals, just like alkali metals. Halogens, they are strong oxidizing agents because they accept electrons. So with metals, they will form ionic compounds, but with non-metals, they will form covalent compounds because they will share electrons. For example, see how the chlorine atoms, neither of them is willing to lose electrons, they want to gain. So they'll rather share electrons, so they have an octet complete, and that's a single covalent bond. That's a chlorine molecule, a stable one. But note, while drawing diagram, the electrons should have been on the orbit and not between them. You don't have drawing in this chapter. Now remember that these halogens are all diatomic molecules, and out of these, bromine is liquid. It's the only non-metal which exists in the liquid state at room temperature. Iodine is solid, although it's sublimatory, and fluorine, chlorine are gases, of course. Fluorine is yellowish in color and chlorine is greenish in color. Bromine is reddish in color. Iodine is violetish in color. Noble gases, of course, have zero reactivity, almost. They are monoatomic molecules, that is, the atom itself is a molecule. So the most important feature of the modern periodic table is that since it is arranged according to increasing atomic number, so now they are easily segregated into groups and periods. So in the same group, you have elements with similar properties, and across a period, you have a transition in their properties, which are repeated after regular intervals. Now let's understand some facts out here. Did you know that Mendeleev had predicted Eka aluminium and Eka silicon because he had left some spaces in the periodic table, and when they were discovered, the properties matched his predictions. Some interesting properties of the transition elements are that they have very high melting and boiling point, they are good conductors of heat and electricity, obviously they are metals, and some of them are attracted towards the magnet like iron, cobalt and nickel. They can be used as catalysts, and as I said, they have variable valencies because they lose electrons even from the second last shell. Now the third period elements, that is all the elements of the third period, are called typical elements because their properties are a representation of the properties of their respective group. For example, sodium belongs to group 1. So if you learn sodium's properties, then you have learned the properties of entire group 1. Now let's look at some trends out here. Let's talk about atomic size. What do you think happens as you go down a group, any group? Definitely the atomic size increases, isn't it? Because the number of shells increases. But the most surprising thing is that when you go from left to right in any period, the atomic size decreases. This you'll study in detail in 10th standard, but it's good to know information that if you look at period number 2, this is period number 2, the atomic size from lithium to fluorine actually decreases, even though all of them have exactly 2 shells. 2 shells, 2 shells, 2 shells. But as the number of electrons is increasing and the number of protons is also increasing, this has just 3 protons in the nucleus and this has 9 protons in the nucleus. So the electrostatic force and the nuclear pull between the positive nucleus and the negative electrons increases. The electrons are pulled with greater nuclear pull. Here there are only 3 protons and 3 electrons. But here, for example, there are 6 protons. So definitely the nuclear pull is greater, so the atomic size decreases. That's not true for noble gases because they are inert, so there's some repulsive force, so that size is a little bigger, so that's an exception. Now let's study some properties of alkali metals. When they react with air, they form the respective oxides. With water, they form the respective hydroxides. With acids, they form the respective salt and hydrogen gas is released. They give you a flame test if you've learned practical chemistry. Sodium gives you golden flame, potassium gives you violet flame, and lithium gives you red flame. These properties are true for alkaline earth metals also, although the balancing will be different because their valency is 2. In order to obtain from their salts, for example, if I give you magnesium chloride, so how will you extract magnesium from it? Well, there's a process called electrolysis. Electricity is passed through the solution to break the bond because their bonds are very strong. It's ionic after all. Inert gases are useful. For example, argon is used to fill the light bulbs so that the filament doesn't burn. If there was air, then the filament, tungsten filament or any other filament will just burn in the air because there is oxygen in the air. Whereas argon is an inert gas, so it will prevent the burning and the filament will last for a long time at such a high temperature. Then there are some neon lights, many colorful lights which are filled with these noble gases, and different gases give different colors. All of them work on the principle of electric discharge, creating light. So the benefits of this modern periodic table is that it's been useful in correcting the past properties of elements, the mistakes made in the past. We can predict the existence of new elements with it. We can study the elements and their compounds systematically. And the position of an element reveals a lot of information to us. Its group number and period number can tell us its atomic number, electronic configuration, number of valence electrons, and its properties.
Hi students, this is AJ sir. If you like this video, press the like button. If you would like to enroll for my online test series or online lectures, email me or message me on Instagram. Check the description for more information.